Hello, my name is Gerhard and I'm a data scientist at SAS and book author for SAS Press. In my data science case studies book, I've also included the case study of how to detect structural changes and outliers in longitudinal data because I have successfully used this method in many customer projects. And this is what I would like to talk today in this webinar. The case study you're seeing here is taken from a larger collection of case studies. So you find case studies on how you can use predictive modeling in, for example, to study the retention of employees in your company, explain forecast errors in time series analysis. I also include text analytics case studies, simulation case studies, and methods of unsupervised machine learning that allow you to let your data talk to you and find interesting patterns. Today we take a look on the case study on how you can detect structural changes and outliers in longitudinal data. We are going to use different analytic methods to do so in order to study course of data over time to see are there certain patterns in the data which you would like to see and which you would like to identify. So the idea to automatically detect breakpoints and outliers is the idea to use machine learning methods to define these points automatically where the course over time deviates from what we might expect as the normal behavior. We will see this to apply multivariate regression splines to identify breakpoints over time, where does the course of the data change, and we also take a look on how you can apply time series forecasting methods like ARIMA models in order to identify points in the data where you have a different behavior from the normal course. Let's start with detecting breakpoints in the data. In this example, we see the recruitment numbers of patients into a clinical trial. You see that this clinical trial has run over quite a long time, starting in 1997 and ending somewhere in 2003. You see from the course over time that in the first years, an average number of patients between 5 and 6 has been recruited into the trial. Then we see a gap and a different level, and finally see a return to the previous trend starting in the mid of year 2000. We would now like to see how analytic methods like breakpoint analysis can automatically find certain points in the data and maybe derive some story behind this. We would now like to see whether we can detect the breakpoints automatically, not by manually investigating every individual picture, but by applying methods that do this automatically for us. We get help here from a method which is called multivariate adaptive regression splines, which is implemented in SAS in the adaptive reg procedure. And this is a method where you use non-parametric regression techniques in order to fit regression splines to your data, and then use a model selection technique to reduce the number of possible breakpoints to a parsimonious, to a model with not too many breakpoints, only those who make the most sense from a statistical point of view. So the idea here is that we study the data and let the data talk to us where such a breakpoint might take place, maybe here and maybe here, and not need to specify the breakpoints in advance. So we would like to learn from the data when a certain change has taken place, and we would like to get an alert or notification that here at this point a certain change in the course of over time took place. Let's take a look how this looks for our recruitment data for the clinical trial. So we would like to see what happened in the clinical trial at certain points in time. We see here the same data as before, from 1997 to 2003. And now we are going to apply the method that I just mentioned. We see when applying the multivariate adaptive regression spline method to the data, in order to fit the model where we would like to see how does the course over time relate to the number of patients, we see that we get automatically identified 3 breakpoints, here, here, and here. These breakpoints are automatically selected by the method and are also inserted automatically into the data here in this graph. And we see in red the original recruitment number from the trial, and in blue the fitted regression spline. Here is linear splines between the breakpoints, where we see a downgoing trend here, an upgoing trend here, and then the final trend until the end of the trial. So after we have now automatically received these potential breakpoints, we would like to investigate them from a business point of view and look back into the clinical trial, whether we see some events that took place there that might explain what happened here. If we study the historic protocol of this trial, we see that at the mid of 1998, one patient had a very severe adverse event, and there was the discussion whether this event might possibly be related to the study medication. Of course, such an event and such an notification always creates a lot of uncertainty into the data, and consequently, over the next months, until this has been clarified and investigated, the uncertainty and has increased, and the trust whether patients should be included into this trial or maybe in other trials has led to a decreasing recruitment number, as you see it here. Only in spring 1999, the study meeting, after investigating the case in a very detailed way, announced that the case that happened here was not related to the treatment, which meant that after this, you see that the recruitment numbers took up again, and you see here some spikes where, as this was a multi-center trial, maybe some of the larger clinics have withheld their patients for a longer time and only now recruited these patients into the clinical trial. And you see that it took almost a year until the recruitment recovers and was back to normal. This is a very nice example to show how data that you observe from a process, adding the method of breakpoint detection to it, can then be explained from a business point of view when we automatically receive the breakpoints. So we see here that without knowing the story before, the method could very well identify the points when the behavior of the recruitment numbers changed over time. Such analysis can also be performed for other data. For example, here for the airline passenger data, where we see the monthly sum of the number of airline passengers between 1999 and 2006. If we study the data, we see a quite strong seasonal pattern for every year. We see an upward trend, and we also see that the event that took place at 9/11 also caused here a downward trend in the number of airline passengers. We can now use the same method as you saw before in order to automatically detect node points and breakpoints in the data. And you see here that the method automatically detects certain points, as you see here. Here in October 91, we have a change in the course of from the early data, maybe a little bit going down, and then we have quite a long period of a steady upward trend. Then we have a small change in July 2000, a larger change in May 2001, and then the downward trend until here. So also for other data, which you see here in a seasonal way, we can see that the breakpoint analysis And the green line you see here is the predicted variable taken from the multivariate adaptive regression splines method. We see that this method can very well identify breakpoints in the data, which we otherwise had to do visually and manually indicate the data, the labels here in the data. In the previous example, we have already smoothed the longitudinal data. This is what I showed with the red line in the previous data. Let's now take a look on how you can smooth longitudinal data, and especially what you have to observe when you smooth longitudinal data. Let's take again a look on the airlines passenger data as we saw them before. You recognize the very strong seasonal trend as you see it here, and for some analysis we would like to get rid visually of this seasonal the deviation and just see the trend over time. In order to do this, you have the chance to smooth your data. And there are two very important methods to smooth your data: backward smoothing and centered smoothing. Let's first take a look on backward smoothing. Backward smoothing means that if we would smooth the data for March 2nd, with a smoothing window of 7 days, we would take the value of March 7 and from this go 7 days back and then calculate the average over the smoothing window of 7 days, looking backward. So historic information until the 2nd of March is used here. The other method, centered smoothing, works the way that you put the actual date you're looking at in the middle and then select a symmetric window here 3 days before, 3 days after, and the day itself, also 7 days window, in order to calculate the average for this number. Let's now take a look what this means if we apply these two methods on our airline passenger data in the previous graph. You see here the red line where I added the backward smoothing method. And we see very nicely that the backward smoothing gives us a good indication on how the trend over the years look like. We get rid of the seasonal pattern, and we also see when the average curve starts reaching a plateau and then falling down after the 9/11 event. This is something which we consider to be a very good smoothing here. Care has to be taken. If we also add a line for centered smoothing to the data, which is represented here as the green line, we see that the following happens. The fact that centered smoothing not only looks into the past, but also looks into the future, because we average values from the past and from the future, we get an indication in the course of the smooth time series already months before the actual event took place. This means that for time series data, you should be very careful when you apply smoothing methods, because only backward smoothing gives you a fair representation of the time series here, because this method only uses the data which has been actually available at this point in time, whereas centered smoothing looks into the future and includes information which is not yet available here. This does not mean that centered smoothing is of no use at all. For example, in geospatial analysis or many other types, the smoothing method with centered averaging is very important, where you would like to balance data from the left and from the right and from other areas. Let's now come to the point where we would like to see how we can automatically detect outliers in our data. The procedure to detect outliers in our data looks as follows. We need to define first what outliers are we looking for. And there's not only one type of outliers, there are different types of outliers, as you see here on the left. There are different types which can be classified in outliers or pulse outliers, where I say at a certain point in time something happens. There's also an outlier type which is called a level shift. I say at a certain point in time, the time series shifts from level 1 to another level and then continues at the new level. There are also other types like a ramp, when the shift from level 1 to level 2 does not necessarily take place at a certain point in time, but over a period. And there's also something like a temporary change. Something changes and it takes some time until this goes back to normal. In the methods that I'm presenting here, I take a look at the first two methods, on pulse outliers and on level shifts. The idea how to perform this is that you fit an ARIMA model to the time series. You can very easily do this in SAS with the X13, the HBF diagnose, or with the TS model procedure. And these methods allow you to automatically identify those points in the time series where the time series deviates from the average pattern. Let's have a look how. You see here again our airline passenger data as before. If we now apply time series outlier detection as we saw before, we would like to find out how are the possible outliers assigned here to the time series, what time points are found in the time series. Let's take a look at that. If we now apply this method, we see that out from the time series procedure we get identified 4 different points in time where events took place. We have 3 level shift events indicated with LS here, and we have 1 pulse event or an outlier event taking place here. So what this does is analytic methods are automatically able to study your data, to learn the pattern like the trend, the seasonal variation, and possible cycles in the data, and then identify those points where the time series deviates from the normal pattern. Of course, we now would like to get this information which we receive in a table here automatically back into our graph. This can be very easily done automatically here in SAS, where I say we would like to take this table which we see here in order to put the reference lines on the appropriate place. So we see, for example, in September 2001, when 9/11 took place, we see a minus of 70 million airline passengers. This is where the drop from here to here takes place as a downward trend. And then we see 2 months later an uprise again for about 6 million. This is when the first shock is over and some passenger numbers go back to normal again. So what we see here is that this method is very useful to automatically identify the point in time, to quantify the magnitude of the change, and also automatically assign it to the time series plot, and also label it automatically. As we see here, the label from here automatically goes also to our graph. In some cases and in some examples, it makes sense to additionally provide more information than just the automatic labels, but maybe you would like to add business interpretations to that. This can, for example, look like this, where I say I label the first one not as September 2001, but I say this is a level shift taking place at 9/11. This is the return 2 months later. This is another pulse outlier here in the data, which is not too dramatically. And here's another shift and a decline at the end of the data, which we see here. So this is another method where you can automatically analyze your data. Let's finally have another look on this decline at the end. This is something which sometimes happens with time series analysis. And you see a decline or a peak in the end, which is very often not caused by the behavior of the process itself, but is very often due to the data collection process. It might be the case that for the last month or for the last few periods, not all data has been collected already and are not available in the data. So it looks like that for the last few periods, you see a downward trend or any other suspicious outliers. Be very careful with over-interpreting these values, because they might just be due to your data collection process and not a change in the data. What I've shown you here is also documented as an example in an article on SAS communities. I show there where, for example, you can simulate time series data which you might need for your analysis with SAS. So I show how you can use a SAS data step in order to add certain features in the data. For example, events, breakpoints, and how you then can use this data to visualize the trend and also automatically detect the breakpoints and the outliers here, and how you can add the labels to it. I will go and add this article collection continuously and also show some examples how you can apply and how you can code the methods that I showed you here. In this case study, you have seen that the important thing here is that you can automatically get help from analytical methods where you see structural changes in your time series data, which you would have otherwise to select manually and review each individual time series one by one. I have used these methods successfully in projects where we study, for example, the course over time from certain counterparts, from our customers, in order to detect points in time automatically where they change their behavior, and we would like to find out what changed in their near history and what might be the real causing event that caused the change in their usage behavior or in other behavior. The important thing is that we get this information graphically, we can review it, but we also get it as lists. And for example, we can order this list to see which customers are extremely suspicious with their behavior and which are not so which are not so far from what we expect from normal. And we also saw that the automatic labeling of these time points is key, because otherwise we had to do this all manually. And we also studied the effect of the smoothing method, where we learned that backward selection is the important smoothing method for time series data. This case study is another example how analytics and data science is here to help you in order to get a clearer, more objective picture about your analysis subjects, and you let your data talk to you and you get the results automatically instead of having to ask each question individually, like searching for the needle in the haystack. The important thing with these methods is that you can do it again, that you can rerun them and treat the models that you have created here as an asset and repeat the analysis all over again. This example and many others are documented in my Applying Data Science book, and also in more webinar recordings like this ones, where I speak on other topics like, for example, text analytics, simulation case studies, survival analysis, or unsupervised machine learning methods. If you're interested in more content, please make sure that you subscribe to the DACH YouTube channel, where I present more of these webinars. I'm happy to stay in contact with you on LinkedIn and on Twitter. And I'm happy if you're interested in content that I present on GitHub and in my SAS Pressbooks.